My name is Drew Sheriff, and I'm going to be explaining Lab 1 for Physics 2211. So the purpose of this lab was to demonstrate Newton's first two laws. First law being if net force is equal to 0, then velocity is constant. Second law is force is equal to ma, mass times acceleration. So there was two models being used. First was the data model on tracker. So basically, the cart was pushed, as you see on the screen, from left to right, and using tracker, you could plot the points over time and determine the velocity. And then I had to pick an interval where the velocity was constant, which would indicate net force equal to 0. And then once I got the interval, I plotted it on GlowScripts by coding. And tracker was the experimental model for proving Newton's laws, and then compared to the theoretical GlowScript model for Newton's laws. We assume that the net force is equal to 0 during this interval because velocity is constant, and no forces of friction or air resistance are acting on the system. The main fundamental physical principles in detail are that the final velocity is equal to the initial velocity plus F net divided by mass times delta t, and the final position is equal to the initial position plus velocity times time. And if the net force is equal to 0, then the initial velocity and the final velocity are the same, and in that case, the position is going to change at a constant rate. A brief preview of the main results. Newton's first two laws were proven to be true because, as we see, this red line is the model of what it should be, and the blue is the experimental data, and they're pretty darn close. So obviously it's not a perfect simulation in the real world, so it's not going to be exact, but it's very close. The system is the cart, and the surroundings are everything else. So the table, the air, everything besides the cart. The initial conditions are for this the time interval chosen, the net force equal to 0 because the velocity is constant. The cart is moving already, so it already has velocity and it is constant. It's non-zero. And then the time is set to 0 during the start of the interval that was tracked. Coding details explained in a clear, logical manner as requested. So the ball velocity is equal to that 0.3364 meters per second because I took the first two frames of recording and I took the average velocity during that time. And since velocity should be the same throughout the whole interval, I chose that for the ball velocity throughout this whole time. And then that was the first arrow. So the second arrow is just the time. It starts at 0, ends at 1.04 seconds. It's just the interval that I chose. The net force, third arrow, is 0, of course, because that's one of our assumptions that we're making. And then the fourth arrow is one of the equations we saw before. So the final ball velocity is equal to the ball velocity plus F net divided by ball mass times delta t. But of course, net force is equal to 0, so the ball velocity is constant. And then the ball position, of course, initial position plus ball velocity times time, so it's going to change at a constant rate since velocity is the same. Similarities and differences between the data and model predictions. The model prediction has a constant velocity, and that's what the experimental should be too, but obviously it's not a perfect world. We can't account for air resistance and friction, so there's going to be a slight deviation from that, but it's pretty close. Sources of error are in plotting the cart mass points, video camera slight movements, and plotting the scale, and the velocity not being perfectly constant. What if the axes were changed? Then the speed would be the same, but the sign of the velocity would be flipped, so it would be negative velocity instead of positive. And we would not be able to determine how many pushes and pulls, how many forces are added together to give 0 net force, because we do not have sensors on the cart to tell us where the forces are coming from.